Chapter 28, number 5. When light strikes glass perpendicularly, about 4% is reflected at each surface. How much light is transmitted through a pane of window glass? Now obviously my light here is not striking perpendicular, but I figured if I tried that perpendicular, then we're not going to see really those arrows very well. So I put it at an angle, but still I keep the 4% is reflected. Okay, so here the light strikes the glass. Part of it is reflected and part of it is refracted. So here's the refracted part. There's some angle, and then here would be the reflected part. There we go. And we could say that that one is 4% if I wasn't writing in black. So 4%, and then 96% is transmitted. But then on the other side we have light being transmitted as well, and here it would be, and then light also being reflected. So here we go. And then again we would have 4% here and 96% here. Now how much is going through here? Well, that would be for the transmission would be 96% of 96%. So we multiply the two. When you do that, you come up with a little bit more than 0.92 or 92%, or a rounded 92%, and with numbers this close to 0, small numbers, that is 4% and 4%, you can simply add the two. 4% plus 4% is 8, and subtract them from 100, so 92% is transmitted. Now somebody could argue, well, this beam here is going to hit the first surface again, and again part of it will be reflected, 4% of that, and then part of that will be transmitted again, but that it becomes so small, it's really just a fraction of a percent, so the answer is 92%. Chapter 28, Problem 9, and when you look in your book, it doesn't exist. I'm making it up in order to get a couple of problems in to talk about the thin lens equation and make a couple of calculations with those. So problem says as follows: you have a convex lens sitting here, and I put the convex lens at 300, at a position of 300 millimeters. And now you take an object and you put the object 129 millimeters away. So notice the position towards the bottom, or 129, oops, totally wrong here. There we go, that's where I wanted to go. 120 is, notice the 171 at the bottom, so that's 129 from the 300. As I said, that's where the lens is, at 300. And then we get an object on the other side, and that object is at a position of, well, 382 or 82 millimeters. Compute the focal length of the lens. So we have DO equals 129 millimeters and we have DI equals 82 millimeters, and now compute the focal length. 1 over F equals 1 over DO plus 1 over DI. And what I'll do on the calculator is that I will type the right hand side in such a way, 1 over 129 plus 1 over 82. Hit the enter button, and then I invert it again because I need to do that for the focal length, because I have to invert again. That's typical mistake that is made, to forget that. And I'll show you what I come up with, a remedy to that. When I do that, I come up with millimeters again. If I have a denominator here in millimeters, denominator here in millimeters, the units stay the same on the right hand side, and it means I also have to have millimeters on the left hand side. Okay, graphing calculator. So it's going to be 1 over 129 plus 1 over 82. Enter. And now if I left the result like that, I would come out with a ridiculous 0.02, and that just can't be correct in millimeters. There is no such length, so I have to invert it once again. Most calculators have this nice inverse button, or if they don't, then just divide 1 by 0.0199, and I come up with 50.1 millimeters, or it looks like we have two significant figures, so round it to 50 millimeters of focal length. And now when I check the applet and click on the lens here, then you see towards the bottom it does say 50 millimeters is the focal length.